All right, let's start with the word of prayer. Dear Lord, thank you for this day. Please help us as we study your creation today with algebraic topology. Help us understand the material. Amen.
Amen.
So, today,
Special or general revelation?
Oh, definitely special revelation,
Okay.
because if you're not a Christian, you can't understand algebraic topology, obviously. That's what we're trying to communicate whenever we pray at the beginning of our videos, obviously. So, this isn't the marker I want.
Thank you, Nathan. That's the perfect answer to that question. Sorry.
Alright, so today we're going to be talking about the fundamental group. So,
Goy.
we'll start with the definition.
Wait.
Oh, you can start with
Alright. So, essentially the idea here, you have two paths, right? So you got F, you have G,
Mm-hmm.
where the end of the first path is equal to the beginning of the second path, and you append them together.
So what do you?
So this here is,
How do you read it besides F star G? Is it?
I guess just F appended to G is how I would read it.
Hmm.
Or I guess,
I think sometimes.
I guess G appended to F, because G
Ah.
is what you're appending on the end.
Yeah. Sometimes I would say something like it's F continued by G or something like that. It's like the continuation of the path F.
Yeah, I guess that works too.
F then G.
F then G.
But so, it's pretty clear here from the gluing lemma
Mm-hmm.
that this is continuous if you have F of 1 equal to G of 0.
Right.
But our goal here is we want to construct a group whose elements are homotopy classes of these paths.
Okay.
So the idea is this eventually, under some identification of paths under homotopy, is going to be our group operation. But before we do that, we need to develop a slightly different version of homotopy than we've been using.
Mm-hmm.
So if you have a subset of x, and you have two functions, f0 and f1, which are continuous from x to y, and you have the restriction of both of the functions to your subset are equal.
Mm-hmm.
And you also have f1 homotopic to f0. Then we write f0 is homotopic to f1 rel A. And the way you say that is f0 is homotopic to f1 relative to A,
Mm-hmm.
which actually, to me, kind of doesn't really make sense. The way I like to think about it is this is a homotopy holding the function fixed on whatever the subset is. But essentially, how we use that in this chapter is we're looking at paths, right? So in our context, I is going to be equal to x. And typically what we're going to take as A is going to be what they call I dot, which is the boundary of the interval. So in other words, it's a homotopy F naught F1 X naught Y naught, holding the two endpoints fixed. So after this we have a theorem. Let's see. Okay,
So
we
it's-
need
so
a
if they're-
definition
So it's stronger than homotopy?
Right, exactly.
Homotopy
Because for
plus-
example, I'm assuming that these are the same points here, so I'm
Okay,
just
yeah.
doing the same drawing. For example, you could have this line here going from x naught to some point y naught, and that would be homotopic to, oh, it's a better way to draw that. Say this is some other distinct point, z naught. In R2, these are both still clearly homotopic, but the values on the endpoints of both functions, this is f1, this is f2, are no longer fixed on our subset here, which we take to be the boundary. So for that reason, it's a stronger notion than homotopy, right? Because essentially all it is, it's homotopy, but each of the functions are required to be fixed on whatever the subset is. So after this, we need another definition. I guess I should probably draw it over here. So we let I be the boundary of the 0, 1 interval as before. Now we define the equivalence class of a path. From I to some space x relative to the boundary I. This is called the path class of f. And we denote this bracket f. So essentially, this is just the equivalence class of f under the relation f homotopic to g rel I dot. And you'll notice that we use the same notation for
Uses
the homotopy class
So we use I
defined
dot-
in the more
I dot
general
is the-
notation.
I dot's just the set containing 0, 1.
Right.
Oh, okay.
I dot's the boundary of the unit interval.
Ah. I missed the. I missed.
Yeah.
I missed the dot. I just missed your words, and I missed the dot at the start. I was like, what? Okay. That's funny. I usually say like partial I or something. You know.
Yeah. Actually, it's interesting. I mean, like in physics, right?
Or BD, like boundary, topological boundary, or.
Like you can use dot to mean
Yeah, dx.
derivative.
Right.
No, I mean boundary. Like when we did a bit of cohomology in advanced calculus, the boundary operator is sort of like the total differential. So it actually kind of makes sense to use this notation
Oh, I see.
as sort of the same way of
I
saying
see.
boundary.
You have justified the notation. I'm with you now.
Yeah.
Because it's one dimensional.
And it's a lot easier to write too
it's-
than
It's one dimensional,
is
so
easier
it's
to
like
write
a
than
time
this,
derivative is just
so-
one dimensional too. That's why it's a dot and not a partial. Partial is for multivariate, but dot is for single variate boundaries.
okay. Well, now you're just getting fancy. So.
Hey, I was raised by physicists. Everything is proved by notation.
Okay.
So this is like a homotopy class, but like with the same endpoints.
Exactly.
Okay.
Yeah. So these two, for example, would be in the same homotopy class,
Path class.
whereas, path class, but these would not. And so the reason we use the same notation,
Mhm.
they say that. I actually don't understand this comment they make here on page 40. It says, no confusion should arise from using the same notation for the homotopy class of a path for its path class because we have remarked that the free homotopy class is always trivial. So I'm not sure exactly where that's coming from, but at the very least, essentially all they use in this chapter is the path class,
Okay.
not the homotopy class, so there should be no confusion with the notation.
Cool.
So, important remark to make before we go on. If you have, let's see, I guess we should do this theorem first. So if you have two paths that are homotopic to each other, relative boundary of the unit interval, and you have the endpoints lining up, right? So I guess I'm writing this backwards, but f naught of 1 is equal to f1 of 1, which is also g naught of 0 and g1 of 1. So essentially,
These are
the endpoints match up so we can compose them, right?
These are loops.
No.
No?
I think
They're just G starts where F ends. Like G naught starts where F naught ends.
Well, but if you have
But there's a quadruple. There's a equals 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 equals.
yeah, you have f naught. Well, hang on.
If you had like F naught of 0 equals F naught of 1,
Oh,
it would
I'm
be
sorry.
a loop, but you don't have that.
We don't have that.
Okay, right.
Ah,
So
okay.
yeah,
So this just makes the endpoints match up.
right. Like the end and the beginning. Yeah. The end of one and
Yeah.
the beginning of the other.
Oh,
So,
we've got,
so these aren't necessarily loops.
so we got four.
They're
We have
just,
4 paths.
I believe you
Yeah,
have
4 different paths.
So it's more like
And you
a.
also had
F naught, F1. I think that's how they're
No,
composing
F1.
it, right?
No.
Or are they composing it the
F1
other
and
way?
F naught ended the same place. So I guess you could, yeah, depending on which direction you're going.
Well,
The second one should be G naught. I think it's more like.
yeah, so I guess they're composing
Oh yeah.
It's like a.
And
F1, G1, right?
yeah, but the
And then
like,
these two are equal?
Yeah.
Yeah.
I think that's all they're saying, right?
F1 starts and ends at the same place as F naught.
Oh, okay.
Because they're homotopic relative.
So it's like a.
So these are actually the same points.
Yeah.
Alright. So if you have that then,
No.
no?
The same. The point that's matching is the middle.
Well,
point.
yes, all 3 points match.
What? The middle point matches. It's like a 4-legged spider.
Yeah, exactly. Well, it's like
Well,
it's like two.
this is, well, okay, so you have f naught of 1 is equal to f1 of 1.
Yeah.
So these points are the same.
Yeah.
Yeah, but they're also
Then-
homotopic relative to the boundary or to I dot. So the beginning's the same and the end's
Oh.
Okay.
the same. So it's really just like two. I don't know what you'd call that.
So, I mean, these are all the same points,
Yeah.
though. So x naught, y naught, z naught.
So it's like a. It's like a balloon with a twist.
Yeah, exactly. It's like a balloon animal, a very simple
Yeah.
balloon animal.
So if you have that then,
Sorry, Nathan.
f naught, what do you say, continued by g naught
You can call it whatever you
is
like.
homotopic to f1
You can call it star if you want.
star g1 relative boundary. So the proof they give here is pretty simple. Essentially, they just construct this homotopy. So they define h of ts to be f of 2ts if t is in the range 0 to 1/2 and g of 2t minus 1s if t is in the interval from 1/2 to 1.
Right.
Where f is a homotopy from f naught to f1, and g is a homotopy from g naught to g1. So let's see, if we plug in 1/2 here for t, we get f of 1s. So that's going to be f1. Or wait, hang on. No, we want to check let's see, I guess to check if it's continuous, we want to look at t equal to 1/2, right? So if we set t equal to 1/2, we get f of 1s, and g of 0s. So g of 0s is g naught, and f of 0s is f1. So I guess that's because these points match up, right?
Yeah.
So then, if we have s equal to 0, you can see that this is just f naught star g naught. If s is 1, you can see it's f1 star g1, right?
Yeah.
Because, for example, f of 2t is 0, g of 2t minus 1, 0. That's pretty much the definition, right? Because then these both reduce to f naught of 2t, and this reduces to g naught of 2t minus 1. So then you can check the others as well, but we don't have much time, so we should move on. So let's see, I should probably erase some stuff. I'll go ahead and erase this, I guess.
Sounds like a plan.
Actually, I should probably be going faster than I'm going now. Because I should have mentioned at the beginning, this chapter is, I think, slightly over twice as long as the one Daniel did last week, or on Tuesday. So I'm going to have to skip.
Do I owe you another day, Nathan?
Maybe, that might be better. But I guess we'll see how far I get today.
You should skip the groupoid proof.
Oh, the groupoid proof? Well, oh, you're talking about the one with the pictures?
Yeah.
Well, I actually worked that on my own, so I wanted to show you guys what I came up with, but let's see. So, essentially, instead of doing this annoying f naught of 1, f1 of 1, etc., they give a definition here if you have a path into x from x naught to x1, they define alpha of the path f to be the beginning.
It's gotta be omega. Is it omega?
Omega, yeah, exactly.
Alright.
Omega of the path to be x1. So, you get path. This is alpha path, and this is
I'm easily amused.
omega of the path. Yeah, so biblical worldview reference of the day, I suppose.
Yeah, alpha and omega, the beginning and the end.
So let's see, then they give the definition. I'm just going to read it. If p is an element of x, then the constant function I sub p with I sub p of t equal to p for all t is called the constant path. Then they define the inverse path. So if you have a path like this,
Yeah.
the inverse path is just given by the mapping t to f of 1 minus t. So, as we've mentioned earlier, these are not just the image, this is actually parametrized. So, if this is f, the inverse of f is something like this, going backwards.
So like alpha of f inverse would be omega
Oh,
of f.
exactly, yeah.
The first shall be last, and the last shall be first.
It's crazy.
Yep. All right. So here we go. Now we have my favorite part. Groupoid. So as I mentioned
Excuse
on
me.
Tuesday, a groupoid is essentially a group
But these homework problems are fun.
where the group operation is not defined everywhere.
Hmm.
So essentially, another way of thinking about it is it's a category where every arrow can be inverted, right? Because you can think if you have topological space X, right?
Mm-hmm.
You can think that as the objects of some category C. And you can think of paths as the morphisms. And so this is like the domain of the morphism then, this is the codomain. And clearly this I of P is the identity morphism for each element of this topological space X. So then we just need to show associativity and that these are actually the inverses, right? So f of x inverse
So you're
is equal to IP.
so you're
But
you're
actually I'm lying because the concept of this category that we're working with, right, that I'm proposing here, is not paths, but actually the set
Right, yeah.
of path classes.
yeah. I was gonna say you're
Category.
divorcing yourself from the actual domain of F and replacing it with just the endpoints of F as being the
Yeah.
when you say it's a mapping from alpha to omega.
Right.
Yeah.
I mean, that's
Path class,
treating
that's all that matters.
the points as objects of the category. Yeah,
So only the endpoints matter, the terminal points. Yeah.
right.
Cool.
So let's see here. Yeah, I don't know how much of this I should go over.
As much as you want.
Yeah, all of it.
All of it. So the first example we give actually is pretty easy to understand, so we'll go over that one. So let's see here. First, they want to show that,
So you're working on theorem 3.2 now, or
right. So first we want to show that I sub p star f. Oh, hang on, did I?
so you might just you don't have to write theorem 3.2, but let's just say it
Yeah.
in words. Theorem 3.2 says if X is a space, set of all paths in X under the not always defined binary operation bracket F bracket G equals bracket of F star G forms an algebraic system called a groupoid with satisfying the following properties. And you're about to prove those properties. Like property
Right.
1 is that the fixed point class, or the I sub p times f is just, what's it called
Right.
again?
Constant.
Constant class. Oh, I guess that makes sense.
Now, hang on, did they actually show, well, I guess theorem 3.1 shows that what they're using as a composition here, think about this as a category, is the operation, well, I guess you're taking path class F and of G
Yeah.
and you're mapping it to
Yeah.
F star G.
Right.
So the theorem 3.1 that we went over earlier shows that that's a well-defined operation.
Okay.
So that's actually the first step.
If alpha
But,
or if omega of F is
Right,
alpha.
exactly, if they're actually composable. So after that, the first step is to show that under this operation, well, I guess that's how they denote the operation.
So no jumps. You can only continue where you ended.
Right.
Okay.
We want to show that this,
So again, this is a groupoid because it lacks closure.
Yes.
right. So this here is what we want to show, right? But another way of saying this is that they're in the same homotopy class.
Right.
Or in other words, these two are homotopic. So to prove this, we want to actually construct such a homotopy, right? So they draw this picture. And this is the square I cross I. So this is 0, 0, 1, 0, 0, 1. And this point here, 1/2, 0. They draw a line from 0, 0 to 1/2, 0. And essentially what they do, they define this piecewise function.
Mm-hmm.
So they define here, which is p, of course, is the value of I sub p at every point, right?
Uh-huh.
And they construct this function omega sub t of s, which you can see this line here has equation 2s equal to 1 minus t. So on this line, let's see, I guess I should write homotopy first. H of s sub t defined to be, like I said, p in this shaded triangle. And they define it to be f of omega sub t of s, otherwise.
If the rectangular monster is in the way of you can give it to me, I'll take it.
The rectangular monster, that kind of makes it difficult to use that part of the board.
Yeah, I mean, you can, if you want to just give it to me, I'll take it.
I thought you were talking about that rectangular monster.
Oh, no, that I don't know what else to do with
Yeah,
it.
you can have this monster though.
Rectangular.
Rectangular, is that what you said?
It's a rectangle.
Oh, okay.
See there, rectangles, turtles that snap.
So if you have 2s equal to 1 minus t,
Yes.
right?
So
That
that-
gives you, let's see. Did I
So
write that right?
whatever you're about to go to also has to be equal to p on that boundary, on that line,
Right.
for the sake of continuity.
So essentially, if you're on this line
Yeah.
and you plug it into this formula, you get p,
Okay.
which you can go
That's-
verify the details of.
And that's f. F of theta t, and the theta t f. I'm sorry if I open. Let me open my book back up. Oh, I see. It's right there on top of page 43.
Right.
Cool.
So then, by the gluing lemma, it's continuous. You can also verify that for, let's see, what is this axis? This is, I should have wrote that, the s-axis and the t-axis, right? So for s equal to 1, you can also verify that you get just straight up
So that goes
f
to
of t.
that goes to f of 0. The glues p glues to f of 0, which is also p by,
Right.
I guess f of 0 has to be p.
Yeah.
Yeah. Because it's a continuation of the constant map p, so it must be that f of 0 is p to do the composing.
So that shows that.
0 for 1.
Oh.
Well, f of 0, it has to be f of 0 here and f of 1 here. But on this line here, it has to be f of t. And if you plug in s of 1, you should reproduce f of t. Right, if you, let's see, they rewrite this.
I mean, when I put in 2s equals 1 minus t into the theta function,
Oh wait, that's 0.
I get 0.
Yeah, that's right. Right, because f continues.
Right, and that f of 0 is p.
Got the ordering all mixed up.
But then when you plug in s equal to 1, you should get f of t.
Yeah, origin of f is p, the end of f is omega is q.
Makes sense.
At least the slanty line part of it. I'm still a little bit bothered by. I like what Daniel said made sense to me for a second. So like f star, so you're doing IP star f. So which geometrically, like f comes first or IP comes first?
IP comes first.
Oh, I hit that
Right,
backwards.
because it's,
Yeah. I did
and like
too.
you were saying,
Oh,
IP
that's why I'm not
continued by
understanding. That's why I
So
wasn't.
it's this
Because
one,
I had the
right?
opposite.
Yeah.
Okay, so it goes to, it starts at P, it ends at P, it's the alpha and the omega of the I sub P, and then the alpha of F is P, which is F of 0. It glues together in the formula because theta of, when you plug in your line, you get theta 0. Theta
Right.
TS is 0.
So then
F
F of
0.
that is P, so it's continuous here.
And then you also need, you said on the right boundary, you need.
Right, if you have S equal to 1, you get F of T. And that shows that these are homotopic.
Okay.
But actually, it's odd. I think it looks like they're using a slightly different formula here. If you look when they actually define H of S comma T, they say this is equal to F of 2s minus 1 plus T over 1 plus T.
Yeah, they.
I mean, so if you multiply both sides by 2, if you multiply everything by 2, you get 2s minus 1 minus T. Is that what they're doing? But that gives you 2 minus... Oh, I think I see it now, right? That gives you 2 minus 1 minus T. Okay.
Mhm.
So then that's just 1 minus T. Well, 1 plus T. Yeah. So then here... Oh wait, did I do that right?
Stupid physics lab. If only there
What
was
did I
some
do wrong?
common area where we could go talk in comfortable chairs nearby.
Minus... yeah. But anyway, we should probably move on.
Yeah.
So this next part here, they give another picture, but I couldn't decipher what they were saying because, let's see. Essentially, after showing you the picture, they say it suffices to show that the continuous map obtained by gluing maps together, as in part 1, is homotopy F star parentheses G star H homotopic to F star G star H rel I dot. But I don't see, from what they gave, exactly what you define on the different regions to make it work.
Yeah, you kind of like have to make your own theta again, I think.
Right.
Like twice.
But in the regions, for some reason, they put F, G, and H instead of F star, G star, H, so... But anyway, I found what I thought was an easier way to prove it that doesn't use pictures.
Yeah.
Michael would approve.
Uh-huh.
So essentially, if you work it out by definition, you can see F star G star H piecewise defined is equal to F of 4t for t in the range 0 1/4, G of 4t minus 1 for t in the range 1/4 to 1/2, and H of 2t minus 1 for t in the range 1/2 to 1. And similarly, you can see F star G star H piecewise defined is equal to 2t g of 4t minus 2 and h of 4t minus 3 for 0, 1/2, 1/2 to 3/4, and 1/2 to 1 respectively.
Oh, I'm sorry, Nathan. There's something I still don't understand. How is it you get? How do you get?
On this one?
Yeah. How do you get t from the? You said you want f of t when s equals to 1.
Yeah, I think it's like when t is equal to 1, you get f of s.
Do I have the variables? I might
No,
have the
variable
variables
right,
messed
but
up.
I think like when you're looking at a homotopy, it's like you want to set t equal to 0 and 1 to see when it's equal to different things, not the first variable.
Right, yeah. I was thinking t was the first variable, I think. So this should be f of s, I suppose, right?
No.
Because t equal to 1. Wait, but they
Right, yeah.
have-
So that would f of s be like the...
I think I might be drawing the picture wrong. Because I had the axes confused.
No, the axes are right.
T, yeah. No, your picture's right. If he's right, I mean he's right.
Hmm.
So.
But anyway, going back to this. So,
If you do t equals
these are
0,
essentially
you get p.
reparameterizations of each other, right?
Yeah. So that's kind of like what they're going for with the picture. It's just...
Yeah, it's just they're
Then
doing
you need
it
to-
visually
yeah.
somehow.
Hmm.
But so these are essentially reparameterizations of each other. So I define the function phi of t to be t over 2, t minus 1/4,
Oh right.
and
Right, I see it now.
2t minus 1. Let's see.
Well, yeah, that's really simple, Nathan. If you just put t equals to 1 in your theta formula,
Yeah.
it just leaves you s
Yeah.
Yeah.
because the 1 minus t's are gone.
Right.
So that gives you f of s. That's all.
Right. Yeah. We were just confused because of the variable thing.
Yeah.
Yeah.
It's cool. It's cool. So you have a direct proof of associativity.
Yes.
You just made a homotopy with 3 cases.
Well, this isn't even homotopy.
What is this?
This is a reparameterization.
Oh.
And so, actually, to prove it this way, you need a lemma, but it's pretty easy to see. If you have a map continuous phi from the interval to the interval, and you have a path from backwards today, I to x, then you can see that f is homotopic to f of phi, yeah. I guess rel I. Well, rel I if it fixes the endpoints. Well, I guess it would have to since it's I to I. Well, not necessarily. But if you have phi of 0 equal to 0 and phi of 1 equal to 1, then they're homotopic, rel I.
You wrote 1 twice. There you go. You wrote phi of 0 equal to 1. But
Oh, thanks. So, once you have that, you have this reparameterization, you can show that f star g star h is homotopic to f star g star h rel I dot, which in terms of our notation up here says that f star g star h
I don't see how that shows up on topic yet.
Well, you don't see how this shows that these two are homotopic?
Right, I think.
Okay, I think, let's see, the homotopy I used, I can show you. I mean, that's a lemma I haven't shown yet.
Oh, okay.
But if you want to see it, I can show it to you.
Yeah.
I think it was,
You should just you go ahead and erase.
Yeah,
you
can you erase the
You can erase
stuff on
the
top?
definition up there, so you can work up there.
okay, I mean, I don't need much space for this,
Oh.
I don't think. But essentially, it's just 1 minus t f of phi of x plus t times f of x is the homotopy you use. So because this is continuous, clearly this is composition of continuous functions. It's continuous. T equals 0, you have the reparameterized version. T equal 1, you have the original version.
Okay, what is f of phi though? Like
F of what?
f of phi of x. Like
Phi is the function I defined. Oh,
what does that say about like g and h in that case?
sorry, I should say, so
Oh, okay. So
F of, you're right, I shouldn't be using F here. You could say this here is like, I don't know what letter to use, let's just call it A. And this here is B.
Okay.
Then
So like a of
A of phi is equal to B. So this you could say is
right. Okay.
A of
I see-
X,
I think
and
I
this
see
you
that
could
now.
say is B of X. So then this shows that A is homotopic to B, or in other words, that F star G star H is homotopic to F star G star H.
I think I'm good now.
Alright. So let's see. I think I lost my place.
Seems like reparameterization's even stronger than.
Yeah, I think it is. I mean, because if you reparameterize, your image is going to be the same.
Yeah.
But that might not necessarily be the case. But it's, I think, easier to prove once you have that lemma. And I think you can pretty much do all of these that way. The last one they
Seems
give,
natural.
let's see, I think
I
now
will,
need
I
more
will tell
board
you this,
space.
Nathan. These pictures are a sore spot for me. It's part of how I got a B in topology.
Oh, yeah?
Yeah.
I mean, that was definitely my experience reading this,
It's B plus. I don't know.
which is why
Yeah.
I came up with my lemma.
I'm quite certain that homotopy question on the final I did bad on. I could not construct the homotopy. So sad. So sad.
And so, the last one they give,
So sad.
we need to show
Too
that
much tutoring.
F star F inverse, like we defined before, is equal to the path class of the identity.
Mm-hmm.
Or in other words, we need to show that F star F inverse is homotopic to the identity for little I dot. So, let's see. They give homotopy here, H of S, S comma T, F of 2S, 1 minus T, 0 in between, or S in between 0 and 1/2. We have 2 times 1 minus S, 1 minus T. So here, if T is equal to 0, you have F of 2S, F of 2 times 1 minus S for these intervals, which I erased the definition, but that is the definition of F star F inverse.
Mm-hmm.
And if you plug in T equal to 1, these go away and you just have I sub P because that gives you F of 0, which is given, I probably should say. for alpha of f is equal to p, right? So that's given. And clearly, composition of continuous maps is continuous, and you can see that it works out on the overlap. So by gluing lemma continuous, and there you go. So this is a groupoid, yay. Alright, so immediately after this then,
Yeah.
they say fix point x naught in x and call it the base point. They define fundamental group of x with base point x naught. They define pi 1 x with respect to x naught, which is just a set of path classes which have f a path and alpha of f is equal to omega of f. So it's sort of like Jesus. Alpha and the omega.
Jesus is a close path.
And that's pi sub 1. So essentially, because everything in here has the same start and end point, everything is composable. So you go from a groupoid to a group. So they just say for the proof of that, this follows at once from theorem 3.2.
Right.
So
Nice.
next we get to the functor pi 1.
Yeah, I don't think anybody can really understand the proof unless they just slog through it bit by bit, you know.
Oh, what's that?
The homotopies, the
Yeah.
thetas and all that. It's just a little bit technical.
I also think
But you can draw a picture, like if you
the technicality,
yeah,
they define that theta map.
yeah,
That's actually an affine map.
yeah,
And I think there's some exercises at the end of the previous chapter dealing with that
right.
that I didn't get the chance to do that may have made it easier to understand. But I guess I should probably erase this too.
Maybe.
Alright.
I mean, those pictures are a standard trick, you know.
Yeah.
Uh,
Alright.
Let's get loopy.
So-
Let's get loopy.
The functor pi 1. Sounds like a movie title or something. So theorem.
When you start mixing your own electronic music, you'll be the functor.
The functor.
My music is categorical.
So pi 1 top star, which you remember is the category of pointed topological spaces and maps. So essentially, there's a topological space together with a point with continuous maps that respect said points.
Right.
So this map is a functor from pointed topological category to groups. So we can already see from what I defined beforehand that pi 1 of topological space together with point is a group. So we need to define a map on the continuous map that sends them to homomorphisms. Then we need to show that the properties of functors are satisfied. In other words, pi 1 of f of g is equal to pi 1 of f of pi 1 of g. So theorem here is a functor. So the big thing is that this sends continuous maps homomorphisms. Well, first we need to define the map on functions. So they say pi1 of h, which later they say is the map induced by h, which I think is a better notation, so I'm just going to use that. Of a continuous map f, they define it by just being the path class. Oh, well, I guess this is path class of f. They define it to be path class of h precomposed with f. So we want to show that h of f star g is equal to h of f star h of g. And so essentially this just comes from the definition of appending maps, right? So this here, this is h of f of 2t, f of 2t minus 1 for t from 0 to 1/2, and t from 1/2 to 1. So if you compose h, it get composed here. So I'm not going to write it, but then you can just write that then as h composed with f appended
For
to
0,
h composed with z,
Yeah.
or
And
g.
It's what then?
It's g of 2t minus 1.
G, oh, thanks. So that's equal to h of f star h of g. So
Yeah.
that's why they just say
Yeah.
it follows that pi1
Yeah.
of h is a homomorphism.
Okay.
So then they say it's routine to check that pi1 preserves composition and identities in top star. I don't know whether that's true or not, but I'm just going to believe them. And so then they say exercise 3.1 shows that h homotopic to k rel x naught implies that h of k of f rel I dot whenever f is a closed path in x at x naught. So that essentially means that we have h of f equal to k of f as well, which implies that pi1 of h is equal to pi1 of k, which actually was the second part of this theorem. If hk, essentially if h and k are in the same homotopy class relative to the base point, right?
Mm-hmm.
Then they induce the same map. So there's that. Then next we have, this is an important theorem.
So what? Just pause for a second here. What would it take to show that the
It preserves composites.
preserves composites or identities?
Well, I can show you that preserves identities pretty
that's
easily.
pretty easy. Yeah.
Because if you have pi1 of, I didn't use the constant map, right? So I sub p, or of
Or
some path,
it's not, yeah,
right?
it's not the constant map, it's the identity.
Well, the identity is the constant map
When
at the point. Well,
we're talking about
no,
functions,
you're right.
Yeah.
here you have continuous maps, so this is
Yeah.
just identity. And we want to show that that maps to the path class of a constant map. So you're right. So if you compose that,
So it's a path class of the identity composed with F, or by definition, right?
um,
Which is the path class of F.
So saying put well, sorry.
Yeah, you said it.
It's a bit much.
That hurts my
Yeah.
eyes.
Well,
Sorry,
by
I have to
definition,
find my other
that's
lasers. So this one's,
yeah. I know you compose with F, right?
it's fun though, right?
Which is just a path for that, which is shows it's the identity.
Fine, I'll behave.
Oh, right.
Go blinding
Yeah.
with lasers. But I will do this.
Ooh, that makes it a little bit harder to point out what you're looking at.
But it's still fun.
Then I guess, let's see, pi 1.
What's that?
Can you see it on camera?
I think you should be able to see it.
On it.
See, now Nathan's all. You've got the green pox. Let's see here.
Yeah, let's look at, see if we can do it. Pi 1 of f of g.
Yeah, I just think it's good to stop and do this because it helps us to understand the definition a little bit more.
So pi 1 of f of g.
I mean, it helps
Oh.
me understand the definition a little bit more. I don't know about you guys, but so we have to.
Of,
You have to feed it something.
I don't know, I guess h.
Well,
That's going to be h precomposed with f of g.
but do
Right.
we want to use the same letters as we were doing before? Because like f and g are paths, and h is the continuous function. So we want like h composed with k.
So h composed with k composed with f.
Yeah, I think that.
Yeah.
Well, yeah, maybe even something different than k, since k. Actually, no, it doesn't matter. We're not there yet.
So this is h of k of f. So we want to show that this is equal to I guess h of f star k of f.
Don't we want to show it's like h composed with k of f, like with the path class of k of f?
Well, it's going to be pi 1 of h of f composed with pi 1 of k of f, right? So then that's the path class of h of f. And that's the path class of k of f.
Got it. Yeah.
Mm. But how do you compose those? Can you even compose those? That doesn't make sense. How do you compose a path class? Right?
Right. Let's see.
See, that's why I was thinking it was star. Well, oh, no, it should be star. Star is how you compose path classes. Right? So we have a functor.
Oh, got it.
Here our
In fact, we don't even write.
composition operator for the functor.
But we don't even write star there.
You don't?
No, because I mean, the his notation is like path class blah times path class
Yeah.
yada is path class blah star yada. So like juxtaposition is what he uses for the product in the path classes,
Okay.
but he uses the star. That is defined to be the path class of H composed with F star K composed with F. I think.
So I guess we have to find a homotopy then between these two. But this then, though, in his notation would be, I mean, by definition of this
Right.
operation here, would be h of f
Because we're trying to meet in the middle.
star k of f.
Doodly doodly.
So we need to show that these two are homotopic.
Exactly.
Oh. But, well, no, that's not quite what we need.
Yeah, because
I mean, yeah, because these are different, so we couldn't use that. It just looks similar.